is not in the session. Okay, now we look at question 17. We look at momentum integration equation. So we start to develop equation for boundary layer using momentum equation. So if you look at the diagram on your hands up or on the screen, we're still using a flat plate with 2 points, point 1 and point 2. And point 1, we will have a uniform flow denoted by capital U. Capital U is our upstream velocity. So at the second point on the top here, of course, we have 100% of our velocity. Here we will have a capital U. And then along this line is our velocity profile. We use a small u. We have this profile because of the viscous effect and then also the friction on the wall here. All right. Just recall that our lift and drag consists of pressure and shear stress. So we'll look at these two components, and then we will have the H denoted as our streamline, and our delta X means our boundary layer thickness in the X function. Means as we increase our X, you see the thickness of our boundary layer. So this means that mathematically we can write sigma or our delta represent our thickness in a function of X because it's changing when we move along X-axis. Okay, and our shear stress also in the X function. All right, so as we move further, a longer surface, then we have a longer shear stress effect. Okay, this is and then we have a control surface here. Control surface, the red dashed line. Okay, these are the basic understanding before we derive the momentum integration boundary layer equation for the flat plate. So how do we develop? Okay, these are the few notes. Okay. Now again, we use the control volume and the control surface equation again for the momentum equation that we learned in chapter 3. So momentum equation start with the V rho dV. V, capital V is velocity. The V with a hat in the middle is volume. So V rho dV times the dt here on the left hand side is for the system, total system, consists of what happened in the control volume and control surface. So this one we already covered in chapter 3, very detailed on each component. So we start with the momentum equation, and in this one we start with the steady flow inside the control volume here. So in X direction, and because it's steady, because we have a steady flow, so automatic you should know that this control volume surface, this component is 0. We only have the second component. So we look at the X component, which is along X. So along X we have 2 points. We have 2 points here. So we pull out the equation. So rho delta UV times the vector magnitude, vector direction, not magnitude, vector direction on the control surface, this one, So we did explain what is in, what is out symbol, right? And dA for section 1, and we include section 2 also. Okay. So we have f-axis for the control system, control surface, right? The concept is that we use momentum equation, and because of the steady flow, this component cancelled, becomes 0. Then we look at the second term here. Second term here consists of 0.1 and 0.2. All right. Now we know that our velocity direction can give us a force, whether it's a lift or drag. So if you look at x direction and the forces is parallel to the upstream, then we are calculating the drag. We are calculating the drag. And in this case, we assume that all direction to the right is positive. So in this case, we assume the drag is opposite it will flow from the right to the left. So from here, we put a negative sign here. Okay, this is what we assume. So in the derivation, we assume that the drag force is opposite of the upstream velocity. In this derivation, we assume that the direction of our drag force is opposite of our upstream. That's why we use negative here. Okay, and given by d equal to negative integration of our shear stress times our dA. So we already explained how we get this equation just now. Why we only have this component rather than pressure. Okay, so that's why if you're not sure, you need to go back to the slides this morning. So on the top, this one is from the momentum equation. On the bottom, this one is from the equation that we learned this morning, which is the drag equation along the x-axis. All right. Then because the A doesn't give us any idea what's happening under integration function, so we need to break the along with dx. Why we need dx? Because our shear stress is in the function of x. That's why we need to break our dA into dx. In this case, is dx. If you flip this is just a side note. If you flip your plates to the y-axis, then your shear stress will be in the y function, and then this equation become dy. This is just a side note. So this is just a interpretation of what we develop from this diagram. Okay, so from momentum equation up to the drag equation. Any question so far? Any question want to ask me? Anything that you're not clear, anything you see on the screen and you're not sure what does that mean, then ask me. Okay, I've assumed, let's see. Okay, Brian's still not here. Brian's still not here. All right. Oh. Okay, we continue. Let me know if not able to see my slides. Sometimes I forget to share my screen. And a B, just a note, B is always represent width of the plate, which is the width of the plate. Okay. This is your P. Okay. Now we have clear what is the drag equation, and then we need to combine with what is the momentum equation. All right. Some side note is that the net force caused by the pressure do not contribute to the flow because of the direction we mentioned just now. Yeah, because the pressure is perpendicular to the upstream velocity in this case, and the plate is solid, and the upper surface of the control volume is a streamline, so there's no flow through this area. So no flow in this area. So we continue with the equation. So we combine momentum equation, this one, and the drag equation. So negative D equal to this whole thing. Then you summarize the equation. So what has been changed if you transfer the momentum equation just now is that the row continue. For the section 1, your U component here you change to the big U. V dot N, it means you need to look at the surface, control surface direction. So in this, for negative because it's going in, negative because it's going in. So we have negative U, and then plus here we have U squared dA. All right, so for section 1, we use a big U. For section 2, we use a small u instead of a big U because this is a viscous, under viscous effect with the velocity profile. So we use a small u in section 2 rather than using the capital U. And then you rearrange the equation. So D become positive, and then the A, of course, you change it to the B times H, all this, right? B times H, this one, dA. So H times B, all right? The area. This is the dA. So you get pH. And then this one, you just change also your dA to B dy here. Because this, we do not know the height, so we just use dy because it's in y direction. Right, here to here is dy, and we have the B, get the area. So we have this one, and we summarize. So dy B, because B is a constant value, we pull out, so we get further reduced from this equation to this equation. Okay. All right. Any question so far? Okay, no question, continue. So I just highlight the H. I highlight the H because normally we didn't see H in our example. I just highlight our H. So because height is very hard to measure, is unknown, so we use the conservation of mass again, which is m dot 1 equal to m dot 2, right? And when this can become incompressible, steady flow, then we can factor density on both sides. That's why we get Q1 equal to Q2, right? So just make a note. So because H is not unknown, and we still want to calculate or want to analyze this problem, we use the conservation of mass equation to continue the calculation. Right. Now, this is just a side note in later steps. So we can write U times H equal to integration of 0 to delta, which is the height here, U dy. Okay. So we can modify this term rho U square BH with our equation here. Right. This on the left hand side is a uniform scenario. This right hand side is viscous effect section 2 area. So we want to make this equation to cover section 2. So we change the H because H is unknown. We want to change into equivalent scenario. So rho U square BH, we substitute this equation inside here. So you will have rho B integration of U small u times a big U dy. Okay, it's a modification of this term into this one. So later we will substitute this one into equation. So you substitute this one in, you rearrange, your drag equation will become D equal to rho B integrate 0 to delta, which is your thickness, boundary layer thickness, U times your upstream velocity, capital U, minus the small u, which is your velocity profile, times the dy. Okay. Why we need to convert this one into this one? Because again, the reason is mathematically we do not know what is our H. So we use the conservation of mass, which is m dot 1 equal to m dot 2. We can write our UH times our dy. Our scenario here will be equal to area under the curve here will be the same. Okay. So we make the mathematics conversion. So at the end we have this equation. And then we recall there is a momentum thickness just now with this symbol like theta, and then with a thick dash in the middle, equal to integration from 0 to infinity, small u divided by u, 1 minus small u divided by u dy. So this equation, the lecture this morning, let me see where is it. It will be in the question 14, 1-4. This equation can be found because we already derived the equation in question 14. So we continue with the definition. So we substitute, we compare this equation to this equation. Then we can write our D equal to rho B U square and our momentum thickness like this. Okay, I skipped the detail steps here. So I just explained how we get this one. So after we get this one, we recall back the definition for momentum thickness. It is, you can find in your tutorial question 14, 1-4. Then you combine this definition, you compare this one and this one. You rearrange mathematically, you will get your drag equal to rho b u square in terms of momentum thickness. And just a remark, d equal to rho b u square and momentum integration boundary layer equation, with this momentum thickness here. This equation is valid for either laminar or turbulent flow, which means this equation is a general equation if you want to analyze drag, right? So in the earlier introduction, when we look at momentum thickness, we already mentioned that every time you see this one is to find drag. You see this symbol, mean this one link up with drag. And this equation is valid for either laminar or turbulent flow. It will be the similar case with our Darcy equation in chapter 3. Okay. All right. Any question for question 17 on the momentum integration equation? This is how we get the equation. If no, then we look at one example in question 18. All right, question 18. Let me check attendance. So Brian's still not here. Huh? Okay, we continue. So we explained about how we get a d equal to rho b u square theta. So now we look at the shear stress distribution. Because in this equation we don't have shear stress, so we want to put shear stress, convert this one in terms of shear stress. So to get shear stress, we put differentiation on this equation. So we differentiate along x-axis. We put d dx, d dx, and on the left and on the right also. So we know that rho b u, we can pull out. We focus on the momentum thickness. So we put the dx over here. Put the momentum into here, because the capital U is the constant value. If you use small u, then you need to dx also, right? But in this case, because in our derivation just now, we have changed all the term in our equation in the upstream velocity. So upstream velocity is a constant value. So left hand side, right hand side, we only can differentiate the momentum thickness and the drag. Recall the definition just now. We have negative d equal to minus b integration of our shear stress times our dx. Right. Of course, the force is shear times area, but area equal to b dx. We pull our b outside already, so that's why here you see dx. Huh? So when you have small changes, we have small changes of drag. From this equation, you can write small changes of d equal to your shear stress times b dx. And then I think if you are good in mathematics, you can see that this equation, how to link with this one already. Right? So here, this equation, how you link with this one, because this equation, you have d dx. So how you transform this one to d dx, you just move this one from right to left, you will have the shear times B for dx, right? So you equalize, you equal these two equations. So left hand side from dx, from d capital D divided by dx, differentiate dx, become shear stress times the B width of the plate equal to our momentum integral boundary layer equation. So just make a note. So from here you cancel out the B because both sides and B cancel out, simplified. So your shear stress on the wall for a flat plate and at this this form. So shear at flat plate give you rho upstream velocity square, momentum thickness, differentiate with x. This form is called momentum integral equation for flat plate. So if you go into higher level, then this equation you can further increase into, you can transform this one into a cylindrical tube or more complex surfaces like sphere, pyramid, and so on. So this is a fundamental illustration, demonstration on flip plate. So later on, when we solve problems, we won't go through all these derivation again. We will straight away use a term called maybe momentum of integration equation. Then straight away you should be able to understand, oh, why we use this equation, all right? Okay, this is important for laminar flow flat plate and also important for your assignment number 1. Okay, let's look at question 18. Question 18. Maybe we'll go for 2 examples up to question 19. Then we go for, then we stop and then we continue on Friday. Okay, let's look at question 18. So what we have here? So we are asked to determine the shear stress by using momentum integral equation. Compare this result with Bayes' results given by this one. So there's some scientists already give a equation. So we compare the momentum integral equation with this one. All right. Consider laminar flow of an incompressible fluid. So if you, I think if you study this module, you'll be happy when you see incompressible because it will always simplify your equation. On a flat plate at y equal to 0, it is here. Boundary layer velocity profile is given. So u equal to uy divided by delta for the height of the boundary layer 0 to delta means from here to here. Okay, your interest area is from here to here. For u equal to upstream velocity big U, for y more than your velocity, your thickness, your boundary layer thickness here. So you have a different u profile, velocity profile. If it's inside the boundary layer thickness, you use this equation. If it is outside the boundary layer, then you use the upstream velocity. Okay, how do we solve this question? Because we want to find the shear stress. So again, pull out the momentum integral equation just now that you learned in question 17, given by shear stress equal to rho u square d your momentum thickness divided by dx shear stress equal to rho u square d, your momentum thickness, divided by dx. So this is what we covered, I think 5 minutes ago. So for laminar flow, because the question state that we looking at laminar flow, we know that our shear stress is given by this equation, viscosity times the velocity gradient at y equal to 0. Huh? So our laminar flow given by this mathematics statement, shear stress equal to mu times del u over del y. Okay, del u over del y. So for assumed profile, we use the definition for the laminar flow just now. We modified the laminar flow equation for shear stress into mu viscosity. U is our upstream velocity divided by your y. Y is your thickness. Recall the momentum equation again, the momentum thickness equation again. This one from this one from 14 also, right? 14. Okay, recall the definition for your momentum thickness. Integration of u divided by capital U, 1 minus small u divided by capital U dy. So with all this, we put all this equation inside here. Right, you simplify, we modify a bit because we want to find this station from here to here. So we integrate 0 to our thickness, our boundary layer thickness, here to here. U divided by U, 1 minus U divided by capital U dy. So we do some modification on this slide. So we first modification, we take the laminar flow definition, link up with the shear stress. We modify accordingly to our case here. And then we call out the momentum thickness, modify the boundary condition, because original is from 0 to infinity. However, in this case, we only interested from 0 to thickness here. Okay. The content still same, only change the boundary condition that we have. Okay, then because you have your U equation here, U equal to Uy divided by delta, because this equation was given for this region only from 0 to delta, because we're integrating from 0 to delta. So our U, small u, we use back the equation here. We substitute this one in, you rearrange, okay? I skip the detail of the calculation. At the end, you arrive at integration of 0 delta, y divided by delta, times the 1 minus y divided by delta times dy. So you can see when you substitute the given equation for the U profile inside the boundary layer, then the equation is further simplified without the capital and even the small u also. There's no velocity content inside here. You only see the y and delta. Okay. All right. Now, so far we only put everything, our mathematic model. We further simplified with the term that we have in the question. Okay. Then if you integrate, you will see that your momentum thickness equal to thickness, boundary layer thickness divided by 6, is it? I cannot see. Yeah, divided by 6. Then you pull all the equation together, we start to build, and then we compare with last year's results. So we have shear stress equation in the momentum differentiate format. We have our wall shear stress definition. We have our momentum thickness that derive for this section. We integrate, we substitute all the value and equation given. At the end, our momentum thickness given by delta divided by 6. So we do not know this value. Yes.
Where we get the 6?
There you get the 6. This one.
Ah.
You integrate this one. You integrate this one, and then because all this y you will have delta. So when you simplify this equation, you will get delta divided by 6. Okay. Yeah. So we combine these three equations, because we do not know the delta. We don't know this thickness value. So we combine everything that we know together, because here you define the shear stress. So on the left hand side of the equation, you substitute with this one. That's why you see mu u divided by this one. And then equal mu u square divided by 6 d delta dx, because this one you put this one in, you dx, you'll get this one. Okay, you simplify further this mathematics line, cancel out the u, pull the delta to one side, x to another side, meaning you rearrange the you set up the equation so that you can integrate later. So the delta, you put the delta one side, dx in one side. This is from this equation. You integrate it, because every time you want to integrate, we will ready our equation in this form. So we integrate left hand side, integrate 0 to delta, again 0 to delta, this region. On the left hand side, so still the same, from 0 to x, right? From 0 to x, because we don't know the distance that we need to calculate. So we just integrate using a parameter x. Okay, so when you integrate, you get this term. This is more on the integration steps. Del square divided by 2. This one you get you will get 6 mu divided by mu u x. All right. So because I'm interested to find the boundary layer thickness, this one. So not integrate. We simplify the equation. All right, 2, and then you square root 3. No, not square root 3. You square root, yeah. No, you square root 12, because 2 left to the right, you get 12. Then square left hand side to right hand side, you get square. So all these term you put together, at the end, the thickness you get is in a term of 3.46 square root of mu x divided by rho u. Okay, so you can change the dynamic viscosity into kinematic viscosity. Right? Just change the dynamic viscosity into kinematics viscosity. Meaning kinematics viscosity equal to mu divided by rho. If you compare directly this equation and this equation. Okay, now this slide is just combine what we learned, these three equations. We group it together. Our objective of this screen is to group it together and then we find what is our delta. What is delta equation? Okay, once we get this equation, we put it back together again. Because we know that our momentum thickness equal to delta divided by 6. So you just take this term divided by 6. You will get 0.577 square root of the parameter. Right. Mu x divided by rho u. And then you do the differentiation because you want to put back into the shear stress equation to compare with the Plus's results. So you put this one and then you dx. So you will get this term u dx. You will get 0.577 divided by 2 square root of mu divided by rho ux. Because this term u dx, so your order of term here is 1 over 2. So your x also 1 over 2. You differentiate means 1 over 2 minus 1. So you will have x minus half. So it will become from the top, then become to the bottom. Right. From here to here is just the differentiation steps. And they explain why your x become from the top to bottom. Put this one back to the shear stress equation. Push this one back. So yeah, when you put back, you will have all this term. This line to this line, because you want to simplify, you want to make the equation a bit tidy, where you pull out the u. So this is the u square, and this is, if you pull out from the square, you will get u power 1 negative half. U negative half, then you rearrange. So your u will have 2 minus half. You will have u power 3 divided by 2. Rho also same. You rearrange the index, you'll get rho half, and then it will be the same like that one. Then you can make comparison already between this one and this one. Okay, you put this one rho back into the equation. You will get rho w, shear, wall shear, equal to 0.289 u power 3 divided by 2 square root of rho mu divided by x. Then you make direct comparison. The one that we built from the momentum integration equation, compare with the Bruss results. So the only difference is in Bruss's equation is 0.332. However, from the momentum, you get 0.289 constant value. Then if you have a question, ask you to compare, then your statement always have the differences will be how many percent. So you make the calculation, the differences in percentage, then you answer the question. Okay. So it's about 30%, 13%. If you compare this number to this number. Right. Now this question is the background of this question was designed to test your understanding and also the application of momentum integral equation. How you apply it to with somebody else experimental results. Okay. So Brian's still not here. Okay. Okay. Any question for question 18? Any question want to ask me? Yeah, just now one question on this one. Del over 6. So you do the calculation, see whether this one correct or not. Right? So anyway, if this one is wrong, the latest answer will still same. You replace back the same. So at the end, you compare the results from what you get, the constant value in front, you compare to the Blasius result, and then you look at what is the difference. Okay. Now this question can become one of the FYP projects. You don't see that this one is a very simple equation, but if you want to really conduct an experiment, this one can become one very big final year research project. Okay. Let's look at question 19. We clear question 19, then we call it a day. Okay, we go one more question. Now, question 19 is a very long question, a lot of equation given. So we start look at the graph first. So there's a graph given, two axes. On the vertical axis, y equal to y divided by your boundary layer thickness. And the horizontal axis is small u divided by u, which is a ratio between the velocity profile inside the boundary layer and the upstream velocity. Okay, and dash will be Laminar turbulent flow. So consider turbulent flow of incompressible fluid passing a flat plate. So our scenario is flat plate, incompressible, and look at turbulent flow. So the boundary layer velocity profile, which is small, assumed to be this one. So because we are looking at turbulent profile, so this equation will be our focus. For y equal to y divided by delta more than less than 1, meaning in this case our y ratio, our capital Y axis here is the ratio between your y and the boundary layer thickness is less than 1, so 0 to 1. All right, and u equal to u for y equal more than 1. So if your boundary layer is above 1 means your velocity magnitude is your upstream velocity, which is U, big U. So it's reasonable approximation, experimental observed profile, a formula given, the change of the velocity gradient, del U over del Y, infinity at Y equal to 0, it is here. Note that the differences between the assumed turbulent profile and laminar profile. So yeah, we see the difference on the graph between laminar and turbulent. Also assume that the shear stress agree with the following equation. So we have the shear stress. Now, what is the question asks us to do? It asks us to determine the 3 boundary layer thickness, because in one of your tutorial question asks which 3 boundary layer thickness often used in boundary layer analysis. So this is application of the question 15, 1.5, asks you about the 3 types of boundary layer thickness. So it asks you from this question alone, it asks you to determine mathematically what is the 3 boundary layer, how you find from this setting. All right, and also, and this data is the momentum thickness. The world shear stress as a function of x, or we need to find we need to change this one in the term of x later on. Determine the friction drag, we need to find the friction drag coefficient. So we know that to find this one, we need to call out the drag equation, and then we rearrange the drag equation to find the drag coefficient, which is we learned this morning. Okay, the strategy to solve this one. Call out the equation for the shear stress in the momentum definition, momentum integral equation. So shear stress equal to rho u square d momentum thickness divided by dx. This is what we covered. This one is in your question 17. The detailed step is mentioned in question 17 in your handout. And again, we call out the definition for thickness equal to this one. We see this one, I think, more than 3 times already. So integration of small u divided by u and the ratio times the dy. We modify a little bit to the question, because in here our dy component is 0 to 1. So we modify this equation to our case here, 0 to 1, u divided by the content of your momentum thickness. To substitute the equation, because we are interested to see the boundary layer region. So in the equation that you developed just now, you have the ratio of u, small u divided by capital U, which is given in the graph here. There's an equation given in the y form, because here you very hard to integrate. There's no y term here, but the graph help you with the y term. So what you do is that you substitute, you take this equation, y divided by the thickness, power 1 over 7. This whole term substitute here, all right, and then cancel out all the similar term, all right. Then you pull out the thickness, dy. So this is from this step to this step, it's just your intelligence in using available data, modified, simplified the mathematics statement. So if you do the calculation, substitute 1 to 0 to 1 in the equation here, you have no longer seen y, you only have a constant value, 7 divided by 72 thickness. You can go and do the detailed calculation later on. Try to understand the steps, what we're trying to do. So in this case, we simplify our momentum thickness equation to a linear equation here. Y equal to mx plus c. So this is our linear equation. Our momentum thickness equal to a constant value times the thickness. Then you pull to the one side and we can start developing our equation. Okay. Pull to one side, you only see these two equations. Shear equal to rho u square d theta over dx. Theta equal to 7 divided by 7.2 delta. So you know that this one you need to integrate with dx. So this you need to put in terms of x function. All right, this one you need to change it to x function. So the momentum thickness, the dx, you put this one in, it becomes 7 divided by 72, the delta divided by dx. Put this one in like a Lego plate. You put this one in, it transform into this one. Shear equal to rho u square times what we developed just now, constant value times the thickness gradient. And you're given the equation just now. With this, the shear stress in a statement under question 19. This one is given, the black color equation is given, 0.225 rho u square, kinematic viscosity divided by upstream velocity times the thickness, power 1 over 4, which is squared 4, equal to what we developed just now. Then the next step is just mathematics equation. Our objective is to get what is our delta. The next step is we want to find what is our delta, right? So we integrate from both sides, from 0 equal to delta equal to 0 at x equal to 0. So we have our delta equal to this equation. So this equation is a dimensionless form. For our thickness. So we have solved the first one. Okay, let's solve the first one. You rearrange, you put this equation in the Reynolds number term. So you pull the del over x, then the rest you rearrange, you get in terms of Reynolds number. Okay. For the displacement of thickness, which is delta x star, and the momentum thickness, again we call back the definition for our momentum thickness equation, equal to integration 0 infinity small u divided by capital U times the content dy. Modified the equation in a question, delta star equal to 0 to 1. Okay. You substitute the definition of u divided by capital U according to the graph here. Substitute back. So you will get your delta, integrate 1, and you only have y term inside your calculation. You do the integration steps. Again, you get a linear equation. Your thickness star equal to 1 over 8 of your boundary layer thickness. Recall the equation of this one. Just now, you already found out what is this one already. You put inside this equation. Put inside this whole definition for thickness. Put inside here, divided by 1 over 8. Right, divided by 8. So your thickness star equal to 0.0463, and the rest will be the same. We have clear for the second thickness star here. Then for the last term here, your momentum, you just again plug in, you'll get your momentum thickness equal to 7 divided by 72 thickness. You substitute what you found for your thickness just now, the lengthy equation. Substitute back here, you will get this term. So you found able to find the momentum thickness 0.360, this term. So this question can further modify to ask you to compare between the boundary thickness of these three. What is the difference between these three? And yeah, so just give you some idea how your final exam can be modified from here. So this slide showing you how you get your boundary layer thickness for the third one. The rest is just substitution. So to find your wall shear stress in a function of x, you just substitute what you find just now. Substitute this one in here. You get this one, very lengthy, but this one later you can follow, you can copy from my slides. The rest is just mathematics. So you write in the Reynolds number if the question asks you to write in the Reynolds number. If not, this already certified to answer the question. And for the drag, we just call out what is the drag from one side of the plate. We already see this equation just now. drag equal to integration of 0 to length, 0 to a length that we interested, B shear stress ds. You put this equation, substitute this one inside here, you get your drag. You integrate your x from 0 to L. You get the equation, this one. Then you pull out the drag equation. So your drag equation that you derive from the boundary layer thickness on the left, drag from the boundary layer thickness, you get 0.0360 rho u square divided by Reynolds number divided by A times A. And this one is a general equation for general definition for drag in the dynamic viscosity, dynamic pressure. Is dynamic pressure, half rho u square CDFA. You combine these two, rearrange in the drag coefficient term. You compare these two, right? Then at the end, you'll get this answer. You compare these two. At the end, your drag coefficient will be 0.720 divided by Reynolds number, 1/5. Okay, so this question 19 explain what you can do with the boundary layer thickness 1, 2, 3. These three types help you to find the drag on the surface. And again, this slide is important for your assignment number 1. Right, your assignment number 1 will be application of what we learned today. Okay, I stop here. Let me check attendance. Brian still not here. Let me stop recording.